Good morning. Today we are going to discuss the colligative properties of solutions. We know that when a non-volatile solute is added to a solvent, becomes a solution, and the vapor pressure of that solution is lower than the vapor pressure of pure solvent. Now, there are many properties associated with this decrease of vapor pressure when a non-volatile solute is added to a solvent. And we call these properties colligative properties. So what are colligative properties? They are the properties of solution containing non-volatile solute. When added to a solvent, that properties depends upon the relative number of solute particles but does not depend upon its nature. They are called colligative properties. So, colligative properties are the properties of solutions containing non-volatile solute which depends upon the relative number of solute particles but does not depend on its nature. That is, these properties will depend upon the number of solute particles present in the solution. Now, there are four colligative properties that we have to study. The first one is relative lowering of vapor pressure. Second is elevation of boiling point of solvent. Third is depression of freezing point of solvent. And fourth is osmotic pressure of solution. So next we are going to discuss each of these properties in detail, and we have a derivation coming under each property, and from the derivations we are able to find an expression. We get an expression to find the molecular mass of solute in solvent. So, we are going to discuss each colligative property. The first one is relative lowering of vapor pressure of solvent. 1. Relative lowering of vapor pressure of solvent. Now, here there are two questions. The first question is, show that the relative lowering of vapor pressure of a solvent is equal to its mole fraction of solute. And the second question is, determine or calculate the molecular mass of a solute from relative lowering of vapor pressure. So, we can say that the relative lowering of vapor pressure is a colligative property because it depends upon the number of solute particles present but does not depend upon their nature. So, relative lowering of vapor pressure is a colligative property. Now, we are going to start the derivation. We know that the vapor pressure of a solution is lower than the vapor pressure of pure solvent. And the relation between vapor pressure of solution, vapor pressure of pure solvent and mole fraction is, that is according to Rawls law, is Pa is equal to P naught A into XA. Now, when you add a non-volatile solute to the solvent, the vapor pressure of solution decreases. So, that reduction in vapor pressure of the solvent denoted by delta P. So, delta PA, because this is the reduction in vapor pressure of the solvent, delta PA will be equal to P naught A minus PA, where delta PA is the reduction in vapor pressure of solvent, P naught A is the vapor pressure of pure solvent, and PA is the vapor pressure of solution. Now, which is equal to, I am going to substitute for PA, P naught A into XA. So, this is equal to P naught A minus P naught A into XA, or equal to P naught A into 1 minus XA. Now, we know that for binary solutions, XA plus XB is equal to 1. Therefore, XB will be equal to 1 minus XA. So, I am going to substitute instead of 1 minus XA, XB. So, you can see delta PA is equal to P naught A into XB, or delta PA divided by P naught A is equal to XB. or instead of delta PA is the reduction in vapor pressure of solvent. Delta PA is equal to P naught A minus PA divided by P naught A is equal to XB. So this is the answer for our first question, that is, show that the relative lowering of vapor pressure is equal to the mole fraction of solute. XB is our solute, and this term P naught A minus PA divided by P naught A is the relative lowering of vapor pressure. So this is the expression to prove that relative lowering of vapor pressure of solvent is equal to the mole fraction of solute. Now the answer for the second question, that is, we have to determine the molecular mass of solute from relative lowering of vapor pressure. So we are going to start from here, that is P naught A minus PA by P naught A is equal to XB. Now we are going to substitute for XB. So P naught A minus PA divided by P naught A. XB is equal to NB divided by Na plus NB, that is mole fraction of solute. Number of moles of solute by total number of moles of all the components present in solution. Now for dilute solutions, NB is very less than Na, that is number of moles of solute is less than number of moles of solvent for very dilute solutions. So we can neglect this term NB in the denominator. So our expression becomes P naught A minus PA divided by P naught A is equal to NB by Na. Now we are going to substitute for NB and Na. We know that NB is equal to given mass by molar mass. It is WB by MB divided by Na is WA by Ma. Or we can write this as WB into Ma divided by NB into WA, or P naught A minus PA divided by P naught A is equal to this. Now you know what each term is. This side is the relative lowering of vapor pressure. WB is the mass of solute in gram. Ma is the molar mass of solvent. MB is the molar mass of solute, and WA is the mass of solvent. Now we are going to get an expression for MB, that is molar mass of solute. So from this expression I am going to write MB will be equal to WB into MA. MB equal to divided by WA into P naught A divided by P naught A minus PA. So this is our expression for relative lowering of vapor pressure, that is MB is equal to WB into MA divided by WA into P naught A by P naught A minus PA. So this expression is used for the calculation of molecular mass of solute from relative lowering of vapor pressure. So if you know all these parameters WB, MA, WA, P naught A and PA, we can calculate the molecular mass of solute. So this is the derivation to find the molecular mass of solute from relative lowering of vapor pressure. Now the second colligative property is elevation of boiling point of solvent. So Roman numeral 2. The second colligative property is elevation of second colligative property is elevation of boiling point of solvent. Now, we know that. What do you mean by the term boiling point? Boiling point is the temperature at which vapor pressure of the liquid equals atmospheric pressure. We know that the boiling point of water is 100 degrees Celsius or equal to 373 Kelvin. So we know that at this temperature, that is at 373 Kelvin, the vapor pressure of water will be equal to the atmospheric pressure, and atmospheric pressure is usually taken as 1 bar or 1.013 bar. Okay, now to this water I am adding a non-volatile solute like sucrose. So we know it becomes a solution now, and the boiling point of solution or the vapor pressure of solution decreases. In the beginning we had only water, that is solvent, the vapor pressure was very high, and now when I added a non-volatile solute, the vapor pressure of solution decreases. Now, if I want to make that solution boil, I should increase the temperature above the boiling point of pure water, that is 373 Kelvin. So that the vapor pressure of the solution becomes equal to the atmospheric pressure. We know that a solution will boil only when its vapor pressure becomes equal to atmospheric pressure. So to make that solution which contains a non-volatile solute to boil, I should increase the temperature above the boiling point of water, that is 373 Kelvin. So we can see that always the boiling point of a solution will be higher than boiling point of pure solvent. So this you have to keep in mind, that is boiling point of solution is greater than boiling point of solvent. Now, let's see the derivation to get an expression for molecular mass of a solute from elevation in boiling point. So you know that when we added a non-volatile solute, the boiling point of the solution increased. So that's called elevation in boiling point. Now, to study the derivation, first we had to plot a graph, and from the graph we will derive an expression for the molecular mass of solute. So the graph, I am going to draw the graph. The graph is between vapor pressure and temperature. Now, look at the graph. The graph is plotted between vapor pressure and temperature. Now, this is the curve for solvent and this is the curve for solution. Now, you can see solvent. This is the boiling point of solvent denoted by T0B, and this point is the boiling point of solution denoted by TB. Now, this is the vapor pressure, that is 1 atm. Now, this difference is our delta TB, that is change in boiling point. Here, in this case, it is increase in boiling point. So, this is the graph for vapor pressure against temperature. Okay, now we are going to start the derivation. So, let T0 be the boiling point of pure solvent and TB be the boiling point of solution. Therefore, increase in boiling point delta TB is equal to TB minus T0B. Tb is the boiling point of solution and T0b is the boiling point of pure solvent. And we know that when a non-volatile solute is added, the boiling point of solution increases than the boiling point of pure solvent. So it is Tb minus T0b. And this delta Tb is called elevation in boiling point. Delta Tb is elevation in boiling point. Now, for dilute solutions, the boiling point is directly proportional to molality. That is, elevation in boiling point is directly proportional to molality for dilute solutions. So, we can write it as delta Tb proportional to small m. It is molality. Or delta Tb is equal to Kb into small m, where Kb is called the molal elevation constant or boiling point elevation constant or ebullioscopic constant. And the unit of Kb is Kelvin kilogram per mole. So Kb is called the molal elevation constant or boiling point elevation constant or ebullioscopic constant. Now, I am going to give this expression number 1. Delta Tb is equal to Kb into small m. Next, I am going to substitute for molality small m. You know that molality is the number of moles of solute dissolved in 1 kilogram of solvent. So, I am going to substitute for molality in equation number 1. So, it will be delta Tb, or I will write the expression for molality. M is equal to Wb divided by Wa into Mb into 1000. 1000 is written when the mass of solvent is given in grams. Now I am going to substitute for molality in equation number 1. Then delta Tb equal to Kb into Wb into 1000 divided by Wa into Mb. From this, I am going to write the expression for Mb, that is molecular mass of solute. Mb is equal to 1000 Kb Wb divided by delta Tb into Wa. So this is the expression to find the molecular mass of solute from elevation in boiling point. Kb is the molar elevation constant and its value will be given to you in the question. Wb is the mass of solute. Delta Tb is the elevation in boiling point and delta Tb is equal to Tb minus T0b, that is boiling point of solution minus boiling point of pure solvent, and Wa is the mass of solvent. So this is the expression to find Mb, molecular mass of solute from elevation in boiling point. Now we are going to discuss, or we are going to get a definition for molal elevation constant, that is Kb. Okay, so molal elevation constant, define Kb. Kb, from that expression we know that delta Tb is equal to Kb into small m. Now, if molality is equal to 1, then delta Tb will be equal to Kb. So, from this you can give a definition for Kb, that is molal elevation constant. It is the elevation in boiling point of solution when 1 mole of a non-volatile solute is added to 1000 gram of solvent. So that is the definition for molal elevation constant or ebullioscopic constant Kb. Okay. Now, this elevation in boiling point can be considered as a colligative property. Why? because here this elevation in boiling point depends upon the number of solute particles, and in this case it depends upon concentration term molality, that is the number of solute particles dissolved in 1000 gram of solvent. So we can call this elevation in boiling point a colligative property. Okay, so with this we finish the expression for elevation in boiling point, molecular mass of solute from elevation in boiling point. Now number 3 is, the third colligative property is depression in freezing point of solvent. So we are going to discuss about that. Number 3, depression in freezing point. Now, what do you mean by freezing point? Freezing point is the temperature at which the vapor pressure of a substance in liquid state becomes equal to the vapor pressure in its solid state. That is, we can say a solution will freeze when its vapor pressure becomes equal to the vapor pressure of pure solid solvent. Now, suppose I add a non-volatile solute. Suppose you consider a ice-water system, ice and water in equilibrium. Now I am going to add a non-volatile solute to this. We know that the vapor pressure of the solution decreases. Now I want to freeze this solution. So I should lower the temperature of the solution, and I should lower it in such a way that it should be lowered, the temperature should be lowered than the freezing point of pure solvent. So we can say that the freezing point of a solution is lower than the freezing point of pure solvent, and we call this depression in freezing point. Now we have to get an expression to find the molecular mass of solute from depression in freezing point. For that we have to plot a graph. Now the graph. This is vapor pressure. Again the graph is plotted between vapor pressure and temperature. Now this is our liquid solvent, and this is solution, and this is the frozen solvent. This is liquid solvent, and this is our solution. This is frozen solvent. Now this temperature, this is the solution curve. So this temperature is the freezing point of solution, and this temperature, this is starting from liquid solvent curve. So this is the freezing point of pure solvent, T0F. And we know that the freezing point of solution is lesser than the freezing point of solvent. And it is also clear from the graph. This TF is the freezing point of solution. Its value is lower than T0F, which is the freezing point of pure solvent. So this is the graph for vapor pressure against temperature for depression in freezing point. Now, again, let T0F is the freezing point of pure solvent and TF is the freezing point of solution. Now, by the addition of a non-volatile solute, there is a decreasing freezing point of solution. Therefore, decrease in freezing point, that is given by delta TF is equal to T0F minus TF, because the freezing point of solvent is always higher. Now, delta TF is called the depression in freezing point. This is our depression in freezing point. Now, for very dilute solution, the depression of freezing point is proportional to its molality. So, delta TF is proportional to small m, or delta TF is equal to Kf into small m. I am going to give this equation number 1, where Kf is called molal depression constant or molal freezing point depression constant or cryoscopic constant. Now, the unit of Kf is also same as unit of Kb, that is Kelvin kilogram per mole. And again, we are going to substitute for molality in equation number 1. So, I will write delta Tf is equal to Kf into Wb into 1000 divided by Mb into Wa. Now, from this expression, I am going to write the expression for Mb. Mb will be equal to 1000 Kf divided by delta Tf into Wa. So, this is the expression to find molecular mass of solute from depression in freezing point. Now, suppose you want to define Kf. You take the expression delta Tf is equal to Kf into m. If m is equal to 1, delta Tf is equal to Kf. So, we can define Kf. Kf is called the molal depression constant. Kf is the depression in freezing point of a solution when 1 mole of non-volatile solute is added to 1000 gram of solvent. Same way, this depression in freezing point is a colligative property because it depends upon molality, that is number of moles of solute dissolved in 1 kilogram of solvent or 1000 gram of solvent. Now, there is an expression given in the book to find the value of Kf and Kb, but usually in problem questions the value of Kf and Kb will be given to you, but still we have to learn that expression, that is Kf and Kb. Kb expression is R into Ma into T0B square divided by 1000 into delta H vaporization. So, this is the expression to find Kb value, and Kf value is R into Ma into T0F square divided by 1000 into delta H of fusion. Now, R is the gas constant, Ma is the molar mass of solvent, T0B is the boiling point of pure solvent. Here T0F is the freezing point of pure solvent, and delta H vaporization, this is the enthalpy of vaporization and this is enthalpy of fusion. So, study these expressions, that is this is the expression to find the value for Kf and Kb. Okay. So, with this we finish the first 3 colligative properties. Thank you.